Hi, everybody. Welcome to Session 2 of Vectorworks Marionette Monday. I'm Robert Anderson, Vice President of Integrated Practice for Vectorworks Incorporated. I'm here with Sarah Barrett, a member of my team and one of our outstanding Vectorworks evangelists. We're really excited to be bringing to Vectorworks users intermediate-level training on our exciting new algorithmic design platform, Marionette. Previously on Marionette Monday. You really don't have to worry if you've missed anything. You can just Google Marionette Monday webinar and get to a recording of our previous session. Let's recap where we are. A quick look ahead is also in order. Today's session is part 2, Marionette Intermediate Techniques. Next week, we'll have our first Marionette Advanced class, and then, 2 weeks later, we'll wrap up formal training with a second advanced class in Marionette. All the classes will be recorded, so you'll be able to go back and pick up the details. We know a lot of you have already. And you'll be notified via email once they're available. Many people asked during the first initial webinar if AI credits were available. We're happy to report this session qualifies U.S. attendees for 1 AI continuing education credit. Instructions on how to self-report will be included in that same recording email. So we want to tell you how to get in touch with us. Whenever you need help, you can always talk with us on our forum. If you want to chat right after this webinar, we'll be there. Or if you ever have a question, we'll be there. And again, a reminder, we have some great Marionette events planned for our upcoming Design Summit, scheduled for April 25th through 27th in Chicago. So you should please make plans to attend if at all possible. You'll get a chance to learn more from Marionette Monday presenter, Sarah Barrett, on this topic. And speaking of Sarah, please join with me in welcoming her as your Marionette trainer for Marionette Monday, Session 2, Intermediate Training.
Thank you, Robert. Now give me a moment to switch our screen over. Okay, so today we're going to talk about the power of lists. Lists are essential to creating complex designs, and we will go over how Marionette handles lists, how they are created, sorted, and parsed. We will also learn some other aspects of Marionette like wrapping networks and creating parametric objects. Last webinar, when we were going through nodes and networks, I was saying what the output values were for each node, but when lists and mathematical operations are used, the output values of nodes can become very complex. As this happens, it can get much harder to figure out what the output values will be without seeing them. Not only can values become complex, but also errors can happen that need to be found and corrected. This is what debug mode is for. So we go to our Marionette tool, and we click on debug mode. We get a small hand icon, and the drop-down menu for getting a Marionette node is grayed out. So with our hand icon, if we hover over wires in our definition, you can see that they highlight red. When you click on a highlighted wire, it shows you, a dialog box opens showing you the values that are flowing through that wire. If the information flowing through the wire is data, you will see number or string values. If the information flowing through is an object, you will see something that looks like this: Vectorworks handle type, colon, and then a number. This is how Vectorworks categorizes different object types. Vectorworks and Marionette refer to objects and scripts as handles. Each object has a corresponding integer and a name that can be used in Marionette definition. To find a list of these types, you can go to the appendix on the webpage developer.vectorworks.net. But we have it right here. So as you can see, in the middle column gives the integer for the type, and the right column gives the string name for the type. So in Marionette, the output of an extrude node is Vectorworks handle type colon 24, as we see here. If you want to know the data coming from a node when no wire is coming out of it, you can use a dummy node. A dummy node you can find in the node library under Debug, and it's the first node in the list. A dummy node does nothing to your network except create a wire from a node that would have not already had one. So if we go back to debug mode, now we can click on the wire and see exactly what's coming out of that rotate. If you click on the wire and get an error message, that means that there is an error in the node in front of that wire or in a node further up the definition. The node must be identified and fixed before the wire can display data. Sometimes when an error message pops up, there is a button that selects the problem node for you. If the error message does not include a button like this, following the errors in the wires backwards can work, just like when you are trying to find the problem bulb in a string of lights, and then changing that bulb will turn on all the lights behind it. So for the sake of error checking, let's go back one more time. Let's change the value of something in our network. Let's change the radius of the sphere to 0. So now we know that a sphere cannot have a radius of 0, so this will probably cause a problem within our network. So we try to run it again, and we get an error report. And then we get this box that makes no sense whatsoever. So if we go back through the wires, we click on this one, we have a value, so we know that that's not the problem. But if we click on this one, an error pops up without a value list. So if we follow that backwards, nope, not that one. Now we know it's from this node. And then we see here, see these little numbers to the right of the outputs? That's telling us how many values are flowing through those nodes. And we probably could have noticed this earlier, but all of these wires have only a 0 coming out of them, which means that they're not doing what they're supposed to be doing. So if we go back and change our radius, now we know that this was the problem. We run it again, you see that those numbers change. We have one sphere and then 15 curves. And then the number 15 continues throughout the wires. So debugging is a term that comes from scripting, and it is simply a synonym for testing. There are several terms and concepts from scripting that we use in Marionette on a regular basis. All of these terms have to do with data, and learning these is the first step in understanding the difference between traditional drafting and algorithmic design. A list is the form that information takes when it passes through your algorithm. Even if there is only one value, it is essentially a list of 1. In scripting, a list is written by putting a bracket at the beginning and end and separating each value with a comma. A list of numbers looks like this. Another way to write a list is to put a new value on every line. This is how lists are written in the dialog windows that pop up when debugging a wire. They look like this. The bracketed numbers on the left are index numbers. Index numbers represent the position of an item in a list. In Marionette, every list starts with an index of 0. In other words, the first value in a list has an index of 0, the second has an index of 1, third has an index of 2, and so on. Index numbers are a way of standardizing your data, just like a filing system. A range is a series of values that go from smallest to largest and have an equal step between them. 1, 2, 3, 4 is a range, but 1, 2, 4, 5 is not, because the steps between them are not equal values. There are 3 ways of creating a range in Marionette, with the nodes range, sequence, and series. All 3 start with the same parameters, the starting value of the range. Then each uses 2 different variables to create a range. As you can see, the range node has the first value and the last value and number of steps. So if we wanted to create this range, 0, 3, 6, 9, 12, 15, 18, if in the range node, we would have the first value of 0, the last value of 18, and the number of steps would be 6. Now this is an important distinction. It's not the number of values, the number of steps. So each step is the space between those numbers. If you think of it as the commas in this list right here. So there are 6. The sequence node has the first two same inputs, the first value and the last value. But this specifies the step value as opposed to the number of steps. So a value of 3, where 3 adds on to each one. And then in a series node, you have the first value again, and then the step value that we used in the last one, and also number of values. And this is talking about each value in the list. Since there are 7 numbers, you have 7 values. There are 5 primitive data types that we use in Marionette. Some of them are standard mathematical terms, but some are specific to programming or scripting. Any raw data that is input into Marionette must be in one of these 5 forms. The first is Boolean. Boolean means true or false. You can also think of Boolean as a light switch or a toggle. It has only 2 options, true or false, on or off, left or right, in or out, even odd, yes, no. You use a Boolean in a network when you want to set up an either-or situation. For example, if my rectangle is 3 meters wide, I want it to be colored green, but if it's 2 meters wide, I want it to be colored blue. That is an instance of where you would set up an either-or situation. There are 2 types of numbers used in Marionette, integers and real numbers. Integers are whole numbers. They are used to represent a position or an entity. Therefore, they can never be fractional. In Marionette, an integer would never need a unit because it is not used to describe size or distance or volume. That is what real numbers are for. Real numbers can be whole or fractional because they represent values. The int node in the input category supplies an integer, and the int node in the math category converts a real number to an integer. The dim and real nodes in the input category both supply real numbers. The difference is dim nodes can supply units that are independent of document units. The float node in the math category converts integers or strings into real numbers. Floating number is another term for real number that is often used in scripting. String is a value that is not a number. It is a letter or a symbol that represents a name or a variable. When you name something in Marionette, the name is a string, even if it has numbers in it. There are 3 nodes in the input category that supply strings: the name node, the string node, and the objects by criterion node. Here. The objects by criterion node uses a string to reference a certain type of object. In this node, the string always begins with t equals, and then the string value for an object type. If we go back to that appendix list, you can see that the string name of the object type is written here as RECT. And so the input for this would be t equals RECT. Points and vectors are coordinates that describe a position in space or a direction. They are made up of real values, and they look like this. They are not necessarily lists. Because they are within parentheses, they are usually treated as a single object. We are familiar with using points in traditional design. And vectors are written the same way as points, but they do not have units because they represent direction. Understanding value types is important for creating a working definition. In this definition, there is a value that is described incorrectly. Let's debug the network in order to find it. So click on any wire, and we get this error message. Float object cannot be interpreted as an integer. So from what we've just learned, what that's saying is there is a real number as an input that should be an integer. So if we go through our definition and look at all of these 5 inputs are real numbers, and one of them shouldn't be. So we see that we have series nodes, and as we mentioned before, the count for a series node always needs to be an integer. So if we replace the real node with the integer node, let's copy the value. Oops. Paste it. And run it, and our network works as it should. Okay, let's go on to data flow. If you remember from the last webinar, the 3 types of nodes that deal solely with data are the data flow nodes, the math nodes, and the point nodes. As you can see in this definition, there are a few input nodes and a single object creation node, and the rest are data flow, math, and point nodes. Although there is only one object creation node in this definition, it is creating many rectangles, as we can see here. If we zoom out and run it. The first section of the network is creating a list of 200 random numbers between 0.1 and 1. It does this by repeating the high and low limits 100 times and sending those numbers into a random node where they get randomized. So we see 100 values of 1 and then 200 values between 0.1 and 1. It then unzips this list into 2, first one value and then the next value in the first list, and so on, until there are 2 equal lists of 100. The next part of the definition creates a series of 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can see by looking at the step, which is 1, and the count, which is 10. And then sending it through a mix2 node and cross-referencing them like we did in the webinar 2 weeks ago. It creates 100 possible combinations between the 2 copies of the same list. This was how we created the point grid in the last webinar. The third part of the definition adds the 2 sets of 100 random numbers to each set of the cross-reference series, and then converts them into x and y values to be used as origin points for 100 rectangles. When there are multiple inputs on a node, and one of the inputs is a list longer than the others, the shorter lists are repeated until the list lengths match. For the rectangle node, there is one default width and one default height, and it is repeated over and over for every origin point that is sent into the node. So, this is what it looks like when we run this definition. But say we wanted to remove the random numbers from this node, from this definition. All we have to do is disconnect these wires. So now the defaults of these nodes will be adding 0 to our series of numbers, and will look like this. You can see the rectangles would be a perfect grid. Data flow nodes can not only create lists of data, but they can also sort and organize data. In this example, we have this group of rectangles that are all different sizes, and we want to identify the smallest and the largest rectangle by area. First, we have to tie these rectangles to our Marionette definition. And the easiest way to attach several objects is to group them and name that group. So I've already done this, and we've given the group a name of rectangle group. And here's the name node that shows this. Next is we want to get to the individual rectangles that are in that group. So we go to the operations category, we get a contents node. A contents node returns the objects inside a container. In this case, our container is a group. And now that we have a node input for this list of rectangles, we need to find out their area. So we can do this by getting a get area node from the object info category. Now if we look at this list of rectangles in debug mode, we can't tell which rectangles are which, but that we don't really need to. No matter how many times we run the definition, as long as we don't change the group, the list coming out of the contents node will not change. And now we have an area for each rectangle. We need to, and we know that the list of area values corresponds to the list of rectangles. So if we want to extract a particular value from the area list, we know it will have the same index number as the corresponding rectangle in the list. So the greatest area value in the list will correspond to the largest rectangle. To find it, we'll use a max item node, which is in data flow category. Attach them. So we're gonna, now that we have this max item, we're going to get an index node from the data flow category in order to get the index that this max item represents in this list. And we know since that index will match the index we want in this list, we attach this list to this node. So what this node is doing is that you're taking in a list and you're giving it a value. Ooh, right, so actually you're giving it this list and you're asking for a value, and it's going to give you the index number of that value. Sorry, I skipped ahead. Now we can use that index number to get the rectangle from this list, because we know that these index numbers match. So for these nodes, we've isolated the rectangle with the largest area. So let's get an attributes node. And give it color. So we can highlight rectangle we want. So run it. And we see that the largest rectangle in the group has been highlighted. So we can do the same thing with finding the minimum number. So let's just go through it quickly. The only difference is instead of getting the max item, we get the min item. And we're going to need a copy of these three nodes. So we're just going to reconnect them the same way we did the max. Let's give this a different color. Run it. Now we see our smallest rectangle has been filled in. So now let's array our rectangles from the smallest to the largest with an even distance between each. First, we don't want to change the original group of rectangles, so we make a copy of the group with our definition. I've already done this to save us some time. You can see here is the network that'll do this. And after the webinar, we'll send out this file that everybody can peruse to their heart's content and look at all these networks in detail. So this time we don't want to use the contents node because that allows the editing of objects without removing them from the container. For this exercise, we want to remove them from the container because we're going to array them. So instead of a contents node, we'll use an ungroup node, which is also in the operations category and does exactly what it says. We'll also use a getArea node again. But this time, we're not going to find a particular area. We want to sort the values from smallest to largest. So to do that, we get a sort node. So a sort node always sorts a list of values from smallest to largest. And if the values are not numbers but are strings, it sorts them alphabetically. So now, we need to find out what the index numbers are for this sorted list. So let's go back to get our index node and our getItem node. So this will give us the index of this list now that it's been sorted. And it will also give us this list with those same sorted index numbers. So now we want a list of points to array our rectangles on. So first, let's get a width node. So just like the area node, this will give you the width of every object that flows through it. And we want to array our rectangles in a line and make sure that none of them overlap. So we want the space between them to be at least as large as the longest width. So let's find our max item again. And now we can use that to create a series of numbers. That will be our array. So this max item will be the step in our array. But now we also need a count. We know that the number of points we need is going to equal the number of rectangles we have. And so there's a way to find this number by using the getListLength node. Any list you put in to this node will return the integer of the length of the list. So we put that into our count. Now, with this series input, we can create a list of 2D points. This is the x value. And we want this array to be near our definition. So if we look at our ruler, we're at 1 foot 8 inches. So let's give our y value a real value of 19 inches. So now we have 2D points that are going to array our rectangles. And we have the rectangles in the order we want them arrayed. So what we don't have are the original points to where the rectangles are in which to move them to these. And we don't have to do it that way. There's a second way to do it. If we go to rectangle category, we get a getRectangle node and a setRectangle node. We put our sorted rectangles into the getRectangle node, and it gives us the sorted list of width and height that we then send to our set rectangle node. So the set rectangle node is basically going to override the parameters that were in the original rectangles with the ones that we put into this node. So we want, again, our original list of rectangles. And then all we need to do is connect our 2D point to the origin of the set rectangle. So if we run it, we have all of these sorted by area and spaced evenly across the page. So, as you might have noticed, in this definition, there was something called a wrapper. And if I click on the inside, you see that there are more nodes inside. So let's talk about how we build those. Actually, first, do we have any questions? Where can we download this random rectangles network? This would really help me with something. As I said, this file will be available once the recorded webinar is available. So all of the definitions that are in this file are workable, usable definitions. So you are welcome to them. I'm also planning on using more random node again in another definition that we'll be looking at next week. How did I copy the 3 nodes? Let's go, where was that? There we go. So basically you copy things the same way you copy them in Vectorworks. You select them and you can do edit, copy, click, edit, paste, or the shortcut for doing this is to select them all and hold down the Option key. You see this plus sign appears, and you just drag them, and it drags a copy of those nodes. Okay, if you have no start input for a series object, does it start at 0? Yes, it does. The majority of our nodes have default values set up in them, so even if you don't put in an input, they can still run. And sometimes they're listed in this description. So if you click on the description button in the OIP, you can see for the series node that if no inputs are connected, the start is 0, the step is 1, and the count is 1. If though that information is not available in the OIP and you really want to know what the defaults are, for example, in a rectangle, they're not there. So we can double click and we open up the script, which is very scary, but as we can see, these lines right here are talking about the input port for width, for height, for orientation, for point. And as you can see within the parentheses, there are values. So the default width for this rectangle node is 1, and the default height is 1. Okay, on to wrappers. So as we're making these definitions, they can begin to look pretty messy. And if you create a network that looks like this, and you come back to it the next day, it can look completely incomprehensible. And if you're trying to share your definition with someone else, you can imagine what his or her reaction would be. Also, there are often certain patterns of nodes that you find you use very often, and it would be a huge time saver to package them up and use them over and over again. This can be done with wrappers. A wrapper is a Marionette network that has been packaged up into a single node. All you have to do to create a wrapper is right-click on any node in the network and select Wrap Marionette Network. And there we have a wrapper node. And if you double-click, you see that definition is now inside the wrapper, and with this orange box, It's similar to what it looks like when you double-click on an object that is a group and has more objects inside it. It works the same way as with other complex objects in Vectorworks. We see that the wrapper is solid white, and that's because it takes on the attributes of whatever class is active at the time. So we can also unwrap it with a right click. Say I want to change the active class to one of the Marionette classes, and wrap the network again. The wrapper will have those attributes that are specific to that class. We can also name a wrapper just as we name any other node. As you can see, its default name is wrapper, and so we can change it to whatever we want. So it could be anything. Sarah's network. But you can see that we have no inputs or outputs on our wrapper. So we couldn't use this with other nodes in another definition. But there is a way to put these inputs and outputs outside the wrapper. And that's, again, by naming. So if we go into our wrapper and we name the attributes nodes, so this node, this color was making us the max rectangle, so we'll call it largest. This one, median. This one, smallest. This one, average. And now we see that we have connections to those 4 attribute nodes on the outside of our wrapper node. We can also make our input nodes available to us. And one way to do that is with an input node. Remember, we usually have something in the OIP that we can edit. In order to make that possible outside the wrapper, you simply name it. So now, with this selected, we see that we can edit the grouped object name in the name node. So maybe I only want to wrap parts of this network. I may use this network again, but I also may want to use different parts of it in other networks. To wrap part of a network, first let's unwrap this. I want to disconnect the section that I want to wrap. So I want to make a wrapper for getting the largest of the area of rectangles. So if I disconnect this, I don't necessarily want to put this in my wrapper because I'm going to need it in other places. So I'm going to make a copy of it and attach it where the original one was attached. And I also want to make sure that my contents is attached to my get area and to my get item. And but I don't necessarily want to copy this node because that's not the. This is a getting information node. This actually has objects in it. So instead of copying the node, we go to data flow, and there is a node that is made just for this purpose. It's called a pass node. And it does nothing to whatever passes through it. It simply allows you to name it to create an input port on a wrapper. So let's change our active class and wrap this. So now we have this wrapper that gets the largest by area. And if we connect it back to the contents, it'll run just like it did before it was packaged. So let's go. Let's see. Now this, I already wrapped a lot of these together to save some time. So this is what that same network can look like, with different parts of it wrapped to make it organized and easy to understand. So this was the same one we created. Now these are the nodes that we use to get a median, and then the smallest, and then to get a 2D center point. So I'm trying to make these names as understandable as possible. And what this actually does, it creates a rectangle. You run it. It creates a rectangle outside of the group that is an average of the size and in the center of where the group is. So we have this wrapper that converts the origin point to the center point, and then we have these wrappers. Now this is the same wrapper, it's just copied. Say I copy the wrapper and I put it in a different part of my network, but then I find out I want to tweak the definition a little bit. So the problem is, if I update this, it won't update the other one because it's a totally different instance. So I would solve this problem the same way I would do this with other Vectorworks objects. I would make it a symbol. So the best way to make it a symbol is to select the network in the wrapper, go to Modify, Create Symbol, and we'll call it AVE for average. Now you can set it however you want, just make sure that Convert to Group is unchecked. That's okay. Exit the Marionette script, and now it works the same way as it did before, but it's a symbol. And if you look at our resource browser, you see there's the symbol. So now we can also, if we copy it, we can replace this one. And say we wanted to change it. We can edit it from here or from inside the wrapper. Say I wanted to change the name of the output to mean. Why didn't that work? There we go. As you see, both of them are updated. So not only can we wrap networks, but we can also convert them into plugin objects. So we go to the network that we made in the last webinar. Remember our point grid inside our polygon. We can wrap this network by right-clicking and wrapping. Then we can go a step farther and we can convert it to a Marionette object. So basically, we can convert this into a plugin object that will have editable parameters, and we can copy and paste just like any other object. So when you have a wrapper, right-click on it, and you'll see Convert to Object node. So now we have that group of locus points that were inside this poly. And if we want to change the number, as you see, it automatically updates the object node. So there's another thing we can do with this, and it's specific to networks that have existing geometry tied to them. So what we can do is we can turn this geometry into control geometry. So instead of right-clicking and converting to object node, if we select both the wrapper and the piece of geometry, then right-click and convert to object node, you see that the poly disappears. Now we have one more step we have to do. If we right-click and edit script, we have this name node, and this was what was referencing the poly in our definition. And we want to change that to a control geometry node. So now that polyline is our control geometry, and again we can change the number of points and it'll automatically update. But what is also interesting about this is if I double click, instead of showing me the script, it turns on the reshape tool. So I can reshape this poly, and as you can see, the grid automatically updates. Any questions at the moment? Can you change the wrapper class without unwrapping and rewrapping? Yes, you can. I only did that. I didn't really need to do that. So you change it just like any other object. When you have it selected, you can change it to whatever class you want. And I have this set so that it isn't tied to the class attributes. That's why it's not changing. Do you only have to select one node in a network to create a wrapper for the whole thing? Yes. If you try to select more than one, you can see that if you try to select more than one, it will let you wrap it. So you can do it either way, but I would, as a rule of thumb, just right-click on one wrapper, whether the whole network is selected or not. Can wrappers with the same name that are not symbols actually be different? And yes. Before we made these symbols, these two wrappers had the same name. So here, let's take one that's not been made into a symbol. And let's change, wait, so I've made a copy of it. And let's just change the name. So I changed this one, and it didn't update this one. So they can each have the same name, but it doesn't necessarily tie them together when they're wrappers. So we're about out of time, but I wanted to go over quickly something that we talked about last webinar, and that's this point grid definition. And someone asked that if instead of getting the points that were inside the poly, what if we want the points that are outside the poly but within the bounding box? So there is a relatively simple way to do this. So in the first definition, we used the points output because it gave us only the points that would have had a Boolean of true. We could have used the Boolean output along with a filter node. And then taken the original points list through the filter node and applied this to the locus node, and we would have gotten the same result. The way we did it with points was just a little shortcut. But now that we have this, we can get the other points. So basically what happened was for every point, if it was in the poly, this list says true. And for every point that's not in the poly, it says false. So in order to make this work with the false values, we need to invert them. So we can do that with an if node. If node is also in the data flow category. And the way an if node works is you put in a Boolean value, just like the filter, and the other two inputs are for what you want to come out of it if the Boolean is true, and what you want to come out of it if the Boolean is false. So we simply want, when it equals true, we want it to equal false, and when it equals false, we want it to equal true. So we get a Boolean input node, and we connect those to the true and the false. Let's connect this Boolean back to this. So now, for the true input, we want it to equal false. And with this input, you see a little checkbox in the word bool. When it is unchecked, that means false. And when it is checked, that means true. So now we have just the inverted list of true and false. And if we run it again, we see the points are outside the poly. So this is all we have time for. I hope you enjoyed this webinar. I hope you got a lot of information out of it. Again, the webinar will be available for you soon in a recorded version, as well as this file for you guys to play with. So I hope that I see you again next week. Thanks for coming.